Good morning, everyone. I hope you
Good
guys are having.
morning.
I hope your
Morning.
February is starting out all right. Um, Guess I didn't get to dismiss that. I'm sorry, I'm closing my email because I don't want that irritation or that interruption. Um, and what I wanted to do first off was I wanted to go ahead and make sure that we concluded everything from chapter one so that we can move on into chapter number two. I'm going to check the chat to see that lots of good mornings. Awesome. Thank you. Now, okay, there was one thing that I wanted to wrap up from chapter number one, and it is a calculation. And then we're going to move on to chapter number two. Um, I have, and this is, please send me, please respond as a private message to whoever has done this. But I've got a notification that someone has requested captions, and if you could please respond as a private message to me, confirming that you can see the captions. And if not, then I don't know what to do right now, but I will get to the bottom of it and get it squared away. Because as far as I can tell, captions. Caption settings. I believe that they are engaged. Captions, just words like closed captioning. Like if you're watching TV or something, show captions. Okay, there, I can see the captions. So, okay, I'm happy to see a response. Um, then one thing I posted, it seems like um, the folks who are in here, I presume that you were able to successfully use the SSO. I'm happy to see that. I wanted to make an announcement regarding the the announcement that I sent on Canvas last night. Um, I just wanted to clarify some things. So the first thing that I wanted to clarify was, and I mentioned this, but I put it in the new syllabus or in the actual typed syllabus. Um, that was in the initial draft of the syllabus, it said if something is submitted late, you have 2 days to submit it, and within that time frame, it will be a 25% deduction. Canvas doesn't have that capability. The way that Canvas has to do it is something will be submitted, and if it's submitted within the first 24 hours after a due date, it'll be a 12.5% deduction. If something is submitted within beyond 24 hours, but less than 48 hours, it will be a 25% deduction. But after that, nothing else will be accepted. And that is true for activities that are forthcoming as well as quizzes. Now, I mentioned the activities because I have not assigned any of those yet, but I will be assigning those in the coming days and in the coming weeks. So that was one thing that I wanted to mention, just kind of clarification on the late policy. The next thing was I had some folks reach out to me and they were curious and maybe a little confused about, hey, how do I get credit for being in class? And the up until now, everyone has received Zoom participation credit. So at this point, everyone's gotten it, even if you haven't been able to come to class. Um, Starting today and moving forward, we'll have Zoom poll questions. And I want you to think about the poll questions as basically like three different types of questions. There will be opener questions, and that's going to be like three, maybe five questions all at once. And that will typically be whenever we're starting a new topic. So we'll get to those in the next, whenever we wrap up chapter number one, you'll have those opener questions. Those will remain open for 5 minutes. Then peppered throughout the class, there will be poll questions. And, typically there's going to be about 3 to 5 of those. Um, and those will be over like, hey, on this slide, we looked at this. Now, next slide is here's a question. And then the last group of questions is going to be the so-called closer questions. Those will be kind of the, hey, what did you learn from this lecture? Did you learn something and can you apply that information? I would say that the closer questions and the mid questions are going to be most similar to your exam questions. Now, That's great for the layout of the class, but how do you get credit for that? So you've got three different things basically. And if you do, let's say that you do the opener questions only, you will get one of the two participation points for the day. Those questions will all pop up at once. And so if you answer all those, you'll get one of the two participation points for the Zoom meeting. Then we've got the mid questions. Let's say that there's three of those and you answer one of them. I'm going to look at that as participation with the mid questions. If you only answer one of those mid questions, well, then you'll get one of the two participation points. Okay, so you missed the openers, you missed the closers, but you did one of the three mid questions. You'll get one participation point for that day. If you do only the closer questions, so you miss the opener, you miss the mid questions, but you do the closer questions, the ones in the last few minutes of class, you'll get one participation point. Okay, so will we have access to the questions after the Zoom meeting closed/ended? There is a way that I can do that, and I will make sure that I get that taken care of so that, yes, you will. You'll have the answers, and I can't remember exactly what I have to do, but I will get into that so that you guys can have those. So to answer your question, Melissa, yes. Now, obviously, you guys want to know, how can I get full credit? Well, if you do the opener questions and you do the mid questions, or if you participate in the mid questions, then you'll get 2 points for that day. Now, what if I miss one of the mid questions? That's fine. There are 3 of them. There are 5 of them. Today, I think we've got 4. Those will all be up for about a minute to a minute and a half each. If you answer one of those, you did a mid question. So if you do the opener plus the mid, you're good. Nailia, we have not done the opener questions yet. We'll do those in just a little bit. Typically, though, when we're on pace, we'll do those at the beginning of the class. And Nailia, I hope I pronounced your name properly. Does it matter if we get it right or wrong? No, it doesn't. Now, I want that to be like a safety net rather than, done. I want you to think about it as like, I'm going to take my chance. And usually I'll have an answer option that is, I have no clue, but I want participation. So here I am. Where do we answer? Do we just submit it in the chat? Cassidy, that's a great question. No, we will not be submitting that in chat. It will be a poll question. It will pop up on your screen. If you're on a mobile device, you might have to hit and I can't, let's see, can I share my screen? I'm sorry for, okay. Oh, wow. I can share the share of my Zoom, which is weird. Okay, minimize. Wait, can I? No, you guys can't see okay. On my screen, there's a button that says more, and there's 3 little dots in it. Will you explain the answers to the question? Yep, that's my plan. So we're going to work through this today, and I will get you your results before our next class meeting. So then if you look at it and you're like, hey, I thought I did all of those, we can, figure out where there were any sort of issues. But in the meantime, what I'm going to do is I'm going to get started on density, which was kind of where we left off the other day. That was the calculation that we're going to get to. If there was a calculation question, can we use calculators on quizzes and exams, or would it be flagged on Proctorio? You can absolutely use calculators and quizzes and exams. I will enable the calculator in Proctorio, so that is a tool that will be available to you. I understand, though, that might be like, well, I don't like using a calculator where I have to click with my mouse. I understand that. That's fine. But to answer your question, yes, you can. This is a private message question. You can use a calculator. Okay, so we have not done any poll questions. So if anyone's looking for them or like, oh, where were they? We have not yet done them. We got to wrap up some chapter 1 stuff, then we're going to move on to chapter 2. Now, what we are talking about today to wrap up chapter 1 is density. Now, density is something that I think you probably have some familiarity with, and you might know it by the term density, but if you don't know it as the term density, I think that there are some good examples that you can think of. For one that I can think of is a styrofoam cup. Now, or I'm going to erase that and say rather than a styrofoam cup, let's just say a styrofoam block. Now, I visualize a styrofoam block as, basically being three-dimensional. And I know that you guys might be like, wow, you're an amazing drawer. I am. And I like to use the term drawer. I don't know if that's the correct word. I don't think that it is. There's probably an English major in this class who's thinking drawer is not a word, sir. But with a block or a brick that's made of styrofoam, that's something that I could like pick up and toss pretty easily. And with that, I could measure the length, the height, and last but not least, this dimension right here, the width. Now, that's got a fixed, or those are fixed measurements, and you could calculate it and come up with something like, oh, well, this is 175. Let's see if each one of these measurements, let's say it was in centimeters, 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 centimeters. Um, could anyone add to the chat? I'm thinking of two letters. What would the units for this block be? What are the density units? And I'll give you a little bit of a hint. My hint is underlined. And if you've ever watched like I don't know, like I know one show I haven't watched. Centimeters is close, right there, but how many centimeters are we doing? We've got three. Ah, perfect, great. CC, or some people will say CM cubed. One new show that I have not yet watched, I know that it's on HBO, is The Pit. It's a medical drama. If you ever hear on a medical drama, or if you've ever been in a hospital setting where someone says like, "Oh, we need 1,000 cc's of saline or 1,000 cc's of a glucose solution," well, that's a volume measurement. Now, density, and I bring up volume because a styrofoam block versus let's say, a masonry brick, also a block, but a brick, a clay brick, let's say that it has the exact same dimensions and it's solid, just like this styrofoam block is. Um, where do we send our 5 responses? Where's we haven't had anything that you guys need to respond to. I got a private message asking, wait, where do we send our 5 responses again? So there we go. Now, between these two, a styrofoam block or styrofoam brick versus a masonry brick, something that's clay, which one of these do you think that you could, let's say you stubbed your toe on one of them. Which one of them would you be like, oh man? And which one of them would you be like, ah? We got A and B. Which one gets the response of ah? A. Absolutely. They're the same volume, but the difference is in the density. And the difference is then the other dimension of density. Okay, so density, I want you to think about this as I'm going to use this term, two-dimensional unit. And what that means is that you can evaluate density based on the volume and the mass. So you can evaluate something based on its, well, the volume, the space that it takes up, as well as the mass. So how much it, for all intents and purposes, think about how much it weighs. So the calculation for density is this right here. D is equal to M over V. So mass over volume. I always like to think of kind of extreme examples. I think about maybe something like a balloon versus a bowling ball. Well, they might occupy the same volume. They might have the same space, three-dimensional space that they occupy. So the volume might be the same, but the balloon, its mass is going to be super low, in part because it's hollow and it's only got air inside of it. Now, the units for density are going to be either grams per milliliter or kilograms per liter. Now, I want you to think about these as kind of being interchangeable. We will most often talk about grams per milliliter, but I also want you to remember kilograms per liter. So if you see that, I don't want you to be like, wait, what? What? Now, one thing that I think is good to think about with respect to these units is, well, could anyone tell me how many grams, so number of G in 1 kg? Add your number response to the chat. 1,000. Perfect. There's 1,000 grams in 1 kilogram. Great job. Now, what about milliliters? So number of milliliters in 1 liter. Could anyone tell me that? And if you need to reference like I don't know, a soda bottle or something like that, I'm seeing lots of 1,000s again. And you're absolutely right. There are 1,000 milliliters in 1 liter. Okay. Now, I like to think about that and draw that comparison because if you then think about, okay, well, you have something, let's say that you've got something that is 1,000 grams and it's 1,000 milliliters. Well, I think you'd, okay, I got a private message question. What's the difference between CC and the units you're talking about now? Okay, I brought up CC as cubic centimeters. I'm going to go back, and I'm sorry for any sort of confusion here. This is a volume measurement. And I apologize, but I neglected to bridge the gap there. 1 cc is equal to 1 milliliter. Sorry about that, and thank you for that private question or private message question. Could you respond if that's helpful? That's good. Because we'll use that as one of the dimensions of density. Great. So if you have a substance that is 1,000 grams and it occupies 1,000 milliliters, I think you guys all have comfort in saying, well, 1,000 divided by 1,000 is 1. Okay. So you could look at this almost as if something has a density of 1 gram per milliliter, it also has a density of 1 kilogram per liter. Now, I bring that up just so you can look at that connection, but I want to stress more times than not, we are talking about grams per milliliter. Okay, now what I want you guys to do in the chat is respond to me. Do you think that this is a physical property or a chemical property? P for physical or C for chemical? Spot on. This has nothing to do with reactivity. You wouldn't say, oh, well, the density of this substance is 14.6, and that really illustrates how reactive this is. So you're absolutely right. It is a physical property. Now, liquids, I think that you probably have some familiarity with liquids with different densities. This right here shows kind of a rundown. Like if this shot glass or this small glass right here has all of these different substances in it. At the top, we've got motor oil, vegetable oil, hand soap, milk, corn syrup, and honey. Now, I'm going to go with H, C, M, S, V, and let's see, O for motor oil. So we got O for motor oil, V for vegetable oil, S for hand soap, M for milk, C for corn syrup, and H for honey. Could you tell me which of these liquids is the most dense? Absolutely. I'm getting lots of responses of H for honey. You're absolutely right. Now, honey has a lot of different properties that you're probably familiar with. One, super sticky. Maybe not the fun thing to like hold on to. That's one property. And I want you to think like, well, the words that you would use to describe something are good examples of physical properties. In addition to it being sticky, well, it's also super viscous. Now, those are great two properties. But honey is the most dense solution. Like if you made tea, If you made chamomile tea as you're going to sleep or something like that, and you added some honey to it, that honey is going to sink to the bottom. The reason for that is honey is more dense than water. Now, these are kind of the non quanti or these are the qualitative descriptions. So more dense, less dense. Okay. Now, we were just looking at calculations, and you can quantify this. You can come up with a number to describe something as being more or less dense. Now, if we look on the next slide, we've got two examples of solutions and their density. Now, the only number with respect to density that I will ask you guys to know is this one right here. Water has a density of 1 gram per milliliter. That is like and this is one thing that's very common in science and in chemistry in particular, is water is like it's a basis for comparison. So it's like the baseline. So everyone will say, oh, well, how does it relate to water? And water's density is 1 gram per milliliter. Now, I want you to think about this, and here's kind of a little bit of a detour. What if you had 4 milliliters of water? So what that means is if we got this right here, this is known as a graduated cylinder, and it can measure up to 10 milliliters. So we got 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Let's say that we added water up to this line right here. We added 4 milliliters of water. Could anyone tell me what would the mass of that 4 milliliters of water be approximately? 4 grams. You're absolutely right. Okay. And if you're ever like, well, how do I figure that out? One way that you can do that is you can use this formula right here. D is our density, 1. That is equal to M over V. Okay. Now, in this example, I gave you the V or the volume. So I'm going to erase that V and I'm going to replace it with the number 4. Well, if I multiply that 4 by each side, that cancels out, and I'm left with 4 times 1 is equal to my mass. Okay, now that's one thing that you can do. I want to now look at that same calculation, but using a different solution. But before we do that, I want to ask you guys, thinking back to this slide right here. Okay, the most dense substance. And I'll go ahead and put a kind of an arbitrary number. Let's say that honey has a density of something like 1.26 grams per milliliter. And motor oil, let's say that that is 0.68 grams per milliliter. Okay, could you give me a W if you follow the numbers and how they relate to density, their relative densities, or a slash if wait, I don't follow that. Okay. So the density, this number right here, this is just sort of it's not a made up number, but I don't know the exact density of motor oil off the top of my head. Same thing goes for honey. What I want you to do though is I want you to look at these numbers and think, okay, well, the most dense substance goes to the bottom of the glass. The least dense substance is going to be at the top, or you could think about it as it floats. Now, with that in mind, let's say that we mixed ethanol and water. And I'm going to draw a little picture. Here's a graduated cylinder. And I'm going to have solution and solution. And I'm going to do another graduated cylinder. Solution and solution. I'm going to give you example A, or option A, and option B. Option A is going to have E, or the ethanol, go to the bottom, and W, or water, go to the top. Option B is going to be water at the bottom, and ethanol at the top. These are two liquids. If you mix them together, and they didn't like mix as a homogeneous solution, but instead they stayed separate, which outcome would you expect? A or B? Add it to the chat. Awesome. I saw lots of people or I saw a handful of folks who put a slash and now they're putting B. So you're spot on. The more dense substance goes to the bottom. And so we've got ethanol that is going to float at the top, water that's going to end up at the bottom. Now, that's great to see. Okay. Now, with that in mind, let's look at this graduated cylinder, and I'm going to erase some of these markings. This graduated cylinder, let's say that, oh, I need the pen function, pen tool. This is approximately, I'm going to say that's about 8.4, 8.3 milliliters. So that 8.3, that is the volume of the solution that's been added. I put a slash because the formula was tripping me up. When we start canceling out numbers, that's what I'm having trouble grasping. I gotcha. Okay. So we're going to work through this one. Now, I'm saying that this is 8.3 milliliters because everyone give me a 1 in the chat if you can see the top of the solution. Okay, great. That's called the meniscus. Now, let's say hypothetically that the solution that was added to this was ethanol. Okay. So that means we added 8.3 milliliters, 8.3 is our volume of ethanol. Now, ethanol typically gets the shorthand notation of ETOH. Ethanol, if you're familiar with that, that is the alcohol that's found in like beer, wine, and spirits and everything like that. I feel like using the word spirits it makes me feel very old because that's at any rate. I don't know why, but it does. So this is the alcohol that's in beer or wine or any sort of liquor. Now, we've added 8.3 milliliters of ethanol to this graduated cylinder. So what I'm going to do is I'm going to say, and my question is going to be, well, what mass is this? And to answer that question, I'm going to go back to my formula. D equals M over V. So I write out my formula. Which values do I have? Well, I've got the density. That's 0.79 grams per milliliter. The volume is 8.3. So I've got the V. I'm done there. Now, as soon as I have 2/3 or 2 of the 3 values in my formula, I kind of got the important stuff that I need. So what I'm going to say there is, well, I'm going to plug in my values. 0.79. And I'll put my units G over ml, but I'm just putting that because I remember those are my units for density. I'm going to set this equal to M. My mass is going to be measured in grams, but at this point I don't know my mass. I'm solving for that. Mass over volume, which is 8.3 milliliters. Okay, so what I need to do is solve for mass. So in order to do that, I'm going to multiply each side by 8.3 milliliters. So when I multiply the right-hand side by 8.3, I need to do the same thing to the left-hand side. That will help me solve for mass. Now, whenever I multiply 8.3 by the right-hand side, I can cancel that out. And that brings me to a point where I have, well, 8.3 times 0.79 is my mass. Oh man, Faith, I'm going to trust that answer. That looks right to me. So thank you very much for that. We get a mass of 6.56 grams. Oh, I got another response of 6.557. I like both of them. They both work. Now, and if you had a exam question, I would not be asking to distinguish between 6.56 and 6.557. So don't worry about that, everyone. Okay. So the sort of question this is a sort of question that I want you to kind of expect to see. But I also want you guys to be able to work in the other direction, where I would give you the density and I would give you the mass and ask you to solve for the volume. So that would be something like, okay, well, you have 13 grams of ethanol, ETOH. You know what? I've got that value written down. I'm going to go ahead and put that in my equation format. 0.79 G over ML. And then that's all over volume. My question here is, what volume would this occupy? If you poured, and this is kind of a weird thing to do, but if you got 13 grams, which whenever I think of mass, I always think of a solid, but does a liquid have mass to it? Does a liquid have weight? Absolutely. If you filled a water balloon with water, it's going to be heavier than a balloon that you just inflate with air. So it has mass. So we've got 13 grams of ethanol. If we were to put that into a graduated cylinder, what volume would it occupy? And to answer this, you'd multiply both sides by V. Those will cancel. Both sides by V. Oh man, that doesn't help us too much. So now what we need to do, and I'm seeing some responses there. Thank you very much, Faith and Stephen. You divide each side by 0.79. So 13, and I'm going to write down here so I'm not writing over stuff. Sorry for that. But 13 divided by 0.79 is going to be our volume, which I'm trusting Faith and Stephen with 10.27. So those are sorts of calculations that I want you to be able to do with this information. So I'm getting a 16.45. Not sure what happened there. I'll plug it into my calculator also just to be on the safe side. So 13 divided by 0.79, and I get, oh wait, I got 16 point, yeah. Okay, sorry about that, everyone. Okay, so 13 divided by 0.79 gives us 16.45. Let me correct that. I apologize. 16.45. Okay. All right, so could you give me on a 1 to 3, one, yeah, I could do this in my head. And a 3, I'm gonna have to do some practice problems. I'd like to see some practice problems. Where do you land on that? Okay, so I can get some practice problems. Density, I'm writing this on my 1310, density PP. Okay, density practice problem. Oh, just so you guys know, Maya, word, I follow you. This would not be a expectation that you do this sort of calculation in your head. I'm just throwing that out there as like, oh yeah, I've got this under control. So, I would not expect that. When I was in graduate school, one of my professors would always come up to people. We were doing lab work, and he'd come up to you and be like, "Hey, um, if you made a solution with this mass of salt and this water, what would the concentration be?" And he'd ask you these questions, and it was like, uh, it was very, very stressful. And yeah, everyone in my lab, we finally got together and like, does Tim ever come up and ask you these mental math questions? And they're like, yeah, he does. Oh man. Okay, so this is an exercise. I'm going to throw this link on the Canvas page so you could do this on your own. Um, because this will give you a way to do this sort of calculation where you're using a solid of an unknown size. So what you would do is you'd put this solid onto this digital balance and figure out the mass of it. Then you can add a solution like water to this graduated cylinder and it would give you a volume. Then what you can do is look at, well, determining the density of a solid based on the amount of water that it displaces. Okay. So if we go back just a tad and we look at this wonderfully drawn brick, okay, you've got the length, width, and height. If you multiply those numbers by each other, three values, three distinct measurements, you can come up with the volume. Um, but as you can see right here, these solids, I mean, I'm just envisioning like a little rock or a pebble that you find. You can't really calculate the length, width, or height very easily of those. So what you instead want to do is determine the volume of water that it displaces. Now, that's a very fun technical way of saying, or if you were to fill a bathtub or fill a pool to capacity, to the brim, and then you got into it, what's going to happen to the water level? What's going to happen to that water in that pool? And maybe a pool's, yeah, it's going to overflow. It'll move up. The level that it rises up is going to be reflective of the volume that you occupy. So that's one of the things that you can do with a solid. Now, here's a question. Density, it's a physical property. And this term right here, intensive property, I want you to be comfortable with that term. Intensive versus extensive. Now, I want you to know that density is an intensive property. What this means is if you had this, let's say that this sheet of, actually, no, I'll change it from, let's say that you had a piece of copper. One that was the size of a penny, and this is 100% copper, and then a different piece that was as I'm looking around my desk for something to compare it to. Um, I'll say as big as your hand. There we go. Um, would they have different masses? Absolutely. The penny's kind of small, but the hand is as big as your hand. The question is, do they have different densities? And the answer to that question is no. Because although these have different masses, do they occupy different spaces or different amounts of space? Absolutely, they have different volumes. So masses differ and volumes, but density is the same. So an intensive property does not change no matter how much of that substance you have. So I'll say no change in density as a result of amount. Could you give me a 1 if that makes sense, or a Z if, wait, that doesn't make any sense. Okay. Okay, great. So to illustrate that, if we had this copper sheet right here, and of course you don't have a scale or you can't visualize that scale, um, and then you've got this nice cube. Okay. Well, the density of these are going to be the same. The volume might be different, and the mass might be different. A good example of this, has anyone ever, give me a Y or N in the chat, has anyone ever gotten a penny and put it on a train track and then picked it up after the train drove over it? If you haven't, it's fun, and the train won't derail or anything like that. But that penny will be super hot right after the train runs over it. And I bring that up because that penny will be completely flattened, and Abraham Lincoln's face is like all flattened out. the density will be the same because the mass of that penny didn't go anywhere. It got flattened out, but the mass stays the same. So the volume changed, or sorry, the volume didn't change. It just changed where everything was. Souvenir penny is another great example of that. I've never gotten a souvenir penny because I no longer am interested in getting one. And whenever I was a kid and wanted one, my parents were always like, no, I'm not paying $1 for a penny. And I was like, it's a good rule of economics, I think. Okay, so to measure density of a solid, we've got this screw right here, has a mass of 29.5 grams. Now we can look at this graduated cylinder right here, and we can see that the volume is approximately, I'm going to call that 35.5 milliliters. Okay, so there's our volume. Now, we want to figure out, is this aluminum or is it zinc? So we're going to say D is equal to M over V. Now, what's really tempting is it's tempting to take this volume right here and plug it in right here. Are we going to do that? Y or N in the chat, please. Nope, we're not. The reason that we're not is because that's the volume of the solution. That is not the volume of our screw there. We are then going to take, but we needed to know this 35.5 because that's our initial volume of our solution. Now, when we take this screw and drop it in, what do we see? We see the volume of our solution go up. And we see it go up to about, I'm going to call that 39.5 is my rough calculation there. So tell me in the chat, what is the volume of my screw? Yeah, about 4. It went from, the volume of solution went from 35.5 to 39.5. So if I wanted to calculate the density of this, it would be, well, mass of my screw, 29.5 grams, divided by 4.0 milliliters. I'll plug this into my calculator to come up with the density. And this is going to help me identify, am I talking about this being aluminum or zinc? So 29.5 divided by 4. Plug it in, 7.375. All right. Now, with that, tell me 7.375. Okay. So I hope that this, and just so everyone knows, whenever somebody adds to the chat, like, hey, I'm lost or I'm confused about this, what I typically try to do is circle back on it and address it one time, like actively in class, and then I proceed. So that way I can kind of explain something 2 times. And if lots of people are like, hey, that doesn't make any sense, that doesn't make any sense, then I'll circle back a 3rd time. But if it's like one person or just a handful of people, please come by my office hours, just so I can kind of keep pacing. Okay. So, but I don't want you to think about that as, oh, he gave me a second shot and then he was done with me. I'm not trying to do that. Okay. So what we want to do is we want to figure out the density of this screw. And we want to figure out, is it made of aluminum or is it made of zinc? That's the problem that we're trying to solve. Aluminum has a density of 2.7 grams per milliliter. Zinc is a different metal, and it has a density of 7.1 grams per milliliter. So what we are trying to do is we're trying to use this metal or use this experiment to figure out what we're talking about. And if you're thinking, well, why would I want to do that? Well, one reason is that these 2 different metals serve different purposes. One of them might be more robust, and one of them might be good if it's never going to be exposed to water, whereas the other one, if it's exposed to water, it's toast. So that's kind of the application of this. Now, the first thing that we do is we figure out the mass of that screw. And that's where this 29.5 grams came from. So we've got this screw on this digital balance, and we have a mass of 29.5. Now, the volume. We can't very well get a ruler and measure the length, width, and height because, look at those those threads in the screw or this where this hex key is going to go. The volume that it occupies is going to be difficult to figure out, but we can do this right here, measure the volume of it by how much water it displaces. This is the similar to, oh, this is the person getting into the bathtub or the pool. The water level is going to rise based on the volume that that person occupies, or that, yeah. So could everyone give me a 7 in the chat if you're good so far and you follow that? And and if you're mixed up on that, then send me a private message with a W. We'll go with that. Okay, so we want to figure out the volume that this screw occupies, and the way that we do that is you take the screw and drop it into this graduated cylinder. So private message question, so are we subtracting displacement from the original volume? We are, because we're looking at what is different between this grad cylinder right here and this grad cylinder right here. The only difference between them is right here, the screw. So we put the screw into here, and the only thing that makes this grad cylinder on the left different from the grad cylinder on the right is the screw is in that solution. So that screw caused the volume of our solution to go up. It caused it to go up from 35.5 milliliters to 39.5 milliliters. Therefore, the volume of our screw is 4 milliliters. So we've got our calculation that we're building. We've got 29.5 grams, 4.0 milliliters, and that gives us our way of calculating our density. 29.5 divided by 4, and that gets us 7.375. And if you look at those two numbers, or if you look at the two values of the metals, aluminum versus zinc, aluminum has a density of 2.7 grams per milliliter. Zinc has a density of 7.1 grams per milliliter. Well, one of these is a little bit closer. And this is a very precise measurement. And could we be more precise? Yeah, if I had this graduated cylinder, I might be able to look a little bit closer and find out more precisely what these values are. But for all intents and purposes, zinc is the identity of this metal that makes that up. Okay, so the next slide really just shows us, hey, you can use density to find mass or volume. You can use this calculation, just rearrange it. We can take our base calculation, D is equal to M over V, and say, oh, well, we're solving for mass. Oh, if we're solving for mass, multiply each side by V, and we're left with. Or if we're solving for volume, what do we want to do? Well, then what we want to do is get volume by itself. Divide this by D. V is equal to M over D. Okay, well, I'm going to end the slideshow for that. And now we are moving on to chapter 2 stuff. But I want to go ahead and post the starter questions for today. So these are our first openers, or I call them openers actually. So these are our first questions. These are kind of what do you know about what we're going to talk about today? What sort of background knowledge do you have? And while that is up, and I'm going to leave that up for about 5 minutes, I'm going to open our slide deck for that. So you'll select your answers and then press submit. There's 3 questions, and we'll go from there. I'll let you just work on it for about a minute and a half, and then I'm going to jump in and start talking. And I repost, I can't repost it, but if you go to your more tab, then that gives you a pull down menu that brings poles up, and you want to click on poles. Okay, so now I'll just tackle these questions one by one. And again, my intention isn't for, oh, well, you got to get it right. I want you to understand this. So the first question reads, a sealed soda can contains liquid soda and dissolved carbon dioxide. The unopened can is placed on a balance and its mass is recorded. The can is then shaken vigorously, but not opened, and its mass is measured again. Okay, so you shake it up. Which statement best explains the result? The mass increases because gas is produced during the shaking. The mass decreases because bubbles form inside the can. The mass remains the same because matter is not created or destroyed. And option D, the mass changes depending on how much pressure builds up. I think all of those are valid answers. The correct answer is the mass is going to remain the same. I answered the first question, then hit submit. I did not know it would make the whole thing go away. That's okay. It happens. Don't worry about it. And I'm in the future just yeah, make sure that you answer all of them. But I know that that probably is motivated by, am I going to get credit? Yeah, you are. Um, a campfire burns 2 kilograms of wood completely, producing ash, smoke, and gases that drift into the air. After the fire goes out, only 0.3 kilograms of ash remains at the site. What happened to the missing mass? So basically, you start out with 2 kilograms, 2 pounds of wood, and you end up with 0.3 pounds. Huh. Well, we've got it was destroyed by the fire, it was converted into energy and no longer exists, it violated the law of conservation of mass, or it left as gases and smoke, but the total mass is conserved. That first one is really tempting. It was destroyed by the fire. That's the first one that I see. But that is not correct because that destroyed is not like what an insurance adjuster would say. Instead, this is like scientifically, was it destroyed? No, it wasn't destroyed. It was converted, but not into energy. Instead, it left or it was converted into gases and smoke. The total mass is conserved. The last question, no matter where you buy it, pure water always has the same mass ratio of hydrogen to oxygen. This is similar to a bakery that makes loaves of bread using exactly 2 cups of flour for every 1 cup of water every single time. This illustrates the conservation of mass, definite proportions, multiple proportions, or Dalton's atomic theory. Okay, so this is trying to bring up things that we're going to be talking about in today. The correct answer is definite proportions. There's a definition. It's almost like there's a recipe. I'm going to leave that question up for another 45 seconds or so that you guys can make sure that you answer it. Now, we're talking about scientific laws. Here, what we have an example of is we've got two solutions. One that is kind of an amber color in a graduated cylinder right here. And then we've got a clear solution. It's tough to see, but it is a clear solution there. Now, if we poured this amber solution into this beaker, what we see happen is a reaction takes place. The amber solution basically gets transferred, and no longer is there something that's amber, it's really more of a reddish copper color. But what I want to draw your attention to is the mass, 173.64. Nothing is lost in that reaction. So what that means is that, when you pour this into here, it's not like bubbles form and, oh, well, there's a gas that evolves. Okay, I'm going to go ahead and end the poll. I'm going to share the results for just a little bit. The most popular answers were the correct answers, so that's great. Now, this is an example of what's on the screen here is an example of the law of conservation of mass. We see that also here. We've got this substance, mercuric oxide. You don't have to know what mercuric oxide is, but I'll give you a little bit of a spoiler. It's a substance made up of mercury and oxygen. Now, if you expose that to a flame, basically give it a lot of heat, what's going to happen is it's going to separate into a solid of mercury. And if you were to capture any sort of gas that's produced, well, that gas would come off as oxygen. Now, if you started with exactly 100 grams of mercuric oxide and this sample didn't have any sort of contamination or anything like that, what you're going to produce is okay, there's these two different substances, but the important part about this is right here 92.61 and 7.39 grams. If you added those two together, 92.61 plus 7.39. Well, okay, so that's zero. That's going to be 7 plus 3, it's 0. 3 plus 7 is going to be 0, and that's going to get us to 100 grams. If you captured everything, well, then it would all be 100 grams. Now, one example that I always think about, um, I have a scale that I stand on. And if I weigh myself before I go to sleep, and then I weigh myself in the morning, um, first question is my weight going to be different, Y or N? Yeah, my weight's going to be different. Okay. Now, next question. Provided that I don't sleepwalk and make myself a sandwich and eat that sandwich in the middle of the night, I think that would be sleep cooking. Provided that I don't sleep cook or sleep eat, is my weight going to go up or down? U or D? Is it going to go up from night to morning? It's going to go down. Now, okay, so we're all on the same page there. How? That's weird. Is it because of the time of the day? Unless I worked out, I could work out. Yeah, it's a good idea. That would be amazingly efficient. If I could work out whenever I was asleep, it'd be great. I burn calories when I sleep. You're absolutely right. Now, let's say, and I don't want this to sound like scary or anything like that, but let's say that I was hooked up to something, and every time I exhaled, there was a bag that would capture whatever I exhaled. Is everyone with me there? Give me a one if you follow, if you visualize this apparatus, or any other key if you're like, I don't see that. Okay. So every time I exhale, whenever I'm asleep, the gas that comes out of my mouth is captured. What if you took the gas plus me and stood on the scale in the morning? What do you think my mass would be, or the combined mass would be? Would it be the same or would it be different? It would be the same because all that I'm doing is my body is metabolizing food and I'm producing carbon dioxide, CO2, a gas is coming out of my mouth while I'm sleeping. So when you sleep and you exhale gas, it's not like you know, did a great workout when you were asleep, but instead the gas that you're releasing is the weight difference from at night and in the morning. Okay. Now, that is an example of conservation of mass. So if a chemical reaction takes place in a sealed container, the mass of the container and its contents are going to be the same before and after. Now, to visualize these sorts of important chemical laws and scientific laws, there's these three big ones that I want you to know. Conservation of mass is an example. We've got here on the left-hand side, we've got a reaction of carbon monoxide, CO, and oxygen, O2. They will come together to make CO2. Now, to visualize those, this is CO, this is CO, and this is O2. Okay, so if you look at that, we've got, I'm going to say 1, 2, 3, 4. There's 4 orange balls and then 1, 2 gray balls. The result is, let's see, 1, 2, 3, 4 orange and 1, 2 gray. So if you look at the reactants and the products, it's not like something magically disappeared or it's not like something magically appeared. These things, these orange and gray balls, are found in equal numbers on the reactants and the product side. So this is conservation of mass. The mass was conserved from the before the reaction and after the reaction. Another important scientific rule is known as the law of definite proportions. That's kind of alluding to that water or that baker's situation where if you okay, um, if you were to go and get a glass of water, that glass of water is going to be H2O. If you get pure water, it's H2O, whether you get it in San Marcos, Texas, in Miami, Florida, or Portland, Maine, or Portland, Oregon. It's going to be H2O. That's definite proportions. Water is always H2O. Now, can water be contaminated? Yeah. But is that water? No, it's contaminated water. Water will always be H2O. Carbon dioxide, visualized here, is always CO2. Now, this last law of multiple proportions shows you that you can take carbon and oxygen and make a substance like carbon monoxide. You could also make CO2, carbon dioxide. The point here is you can take building blocks and build different things. Are these the only compounds that have only carbon and oxygen? No, they're not. There are others. There are others that also have hydrogen. You can arrange, and another example of that would be H2O2, which is hydrogen peroxide, versus H2O. Drinking H2O, good idea. Drinking H2O2, hydrogen peroxide, bad idea. Don't do that one. Okay, now this is going to bring us to our first mid question. This question reads, the composition of water always yields 88.8% oxygen and 11.2% hydrogen by mass, which illustrates the law of conservation of mass, the law of definite proportions, or the law of multiple proportions. Now, I'm going to leave that up for about 10 more seconds, and then I'll start explaining it. So we've got, take a drink. Okay, so we've got 68% of the class responding. Conservation of mass. Whenever you see that, I want you to think before something, I'll say before a reaction and after a reaction. RXN is kind of a shorthand way of writing reaction. It said failed to submit for some reason. Okay, well, we're going to do some more of these, so make sure that the others go through it. And I know that you're making sure, but in the event that they don't, please email me or we'll talk after. So conservation of mass is a comparison. So always think about that as like, well, this right here, it produces 88.8% oxygen and 11.2%. It doesn't describe something happening, an event happening. The law of definite proportions. I always try to think about this as, are we defining something? And whenever I think of defining something, I always kind of think about it or try to think about it as, well, this is a definition that people are going to need to know. This response or this question, the composition of water, it's telling you, here is the composition. So, okay, that's a definition. So our correct answer here is law of definite proportions. I'm going to go ahead and end this poll. Our most popular answer was the correct answer. Now, the next mid question that we're going to do, I'm going to stop the share. I'm going to show you this next question, is there are different oxides of iron. For a fixed mass of iron, the masses of oxygen in three oxides give the ratio 6, 8, and 9. Okay. Now, this one, we've got conservation of mass. And give you a little spoiler. There's only been one response that says conservation of mass, and you guys are collectively on the right path there. Okay, so I'm going to go ahead and cross this out because this doesn't tell us or it doesn't give a comparison before something happens and after something happens. So we can eliminate that. So that gives us B and C, the law of definite proportions or the law of multiple proportions. Okay, these are kind of tricky. They both have to do with defining something. But I want you to think about multiple proportions. And whenever you think about that, I want you to think about H2O versus H2O2. If I were to tell you about these things, I would say, well, water is this. And then if I were to say, oh, but H2O2 is different, I would say this is hydrogen peroxide. I'd say, oh, this is when I was in high school, this was really good for bleaching your hair. And it was a weird time. People liked Limp Bizkit and Kid Rock. Um, with that, though, multiple proportions. It's the same atoms being combined in different combinations. So this would be C, law of multiple proportions is the correct answer. I'm going to go ahead and end the poll for that one because we got another question coming up in just a second. Actually, I'll wait until 2 minutes. Now, there was all of this kind of comes together, and the important parts about this come together in what's known as Dalton's atomic theory. Now, Dalton's atomic theory, we've got 2 more mid questions, then we got closers, and we are doing just fine on time. Dalton's atomic theory, you could sum this up in a couple of different ways. And these modern modifications are kind of the summary of what they mean now. So, number 1 says Dalton assumed atoms to be indivisible, but atoms are divisible. So, this says that atoms, there are what are known as subatomic particles. And we'll get more into those after a little while. Dalton assumed that all atoms of a given element were identical in respects, including mass. We now know that this is incorrect due to subtleties in subatomic scale. So what this means is that atoms of H, hydrogen, are different. They differ from atoms of carbon. Now, the important ones that I want you to take away from this are numbers 3 and number 4, or actually really just number 3. Dalton's theory from hundreds of years ago is that compounds are formed when atoms of different elements combine in fixed proportions. This one is the multiple proportions. So what I want you to think about with respect to scientific laws, and if you're like, oh, what's a good slide that I should really commit to knowing? It'd be this one right here. No conservation of mass, no definite proportions, and distinguishing that from multiple proportions. So this slide right here, which is slide number 6, is a really good one for you guys to be comfortable with. Okay, now next up is the periodic table. Okay, so we're going to get into like what makes the periodic table and what makes it tick. So whenever you look at the periodic table, you're going to see a couple of different things. You're going to see an atomic number. What I want you to notice about these 2 numbers and how they differ from one another is that the atomic number is a whole number, no decimals. Your atomic mass, by comparison, has decimals. So when you look at the periodic table, you're going to see those 2 numbers. Those are maybe the most important and prominent ones. And then you're also going to see a symbol. For example, Fe is a symbol for the element iron. Now, what all of this tells us, or what all these things tell us, are a couple of different things. One, the atomic number tells us how many, or tells us the number, scribble that out, number of protons. Okay. And then the atomic mass tells us the mass of one atom of this element. Now, This mass is going to vary a little bit, and we'll get more into that after a little while, but um, I want you to know this and know this as the units for this are AMU, which stands for atomic mass units. So we've got atomic number, which tells us the number of protons. A proton is a subatomic particle. The atomic mass tells us the mass of one atom of this, and the units are atomic mass units, or AMU. Okay, now I'm going to jump ahead and then I'm coming back to the mid question. This is an example of the periodic table. Here, what you can see in this particular model is you can see the symbol and then the atomic number, but this one does not have the atomic mass. A good resource for the periodic table, to me, for all of you guys to look at, is www.ptable.com. That's a great resource because it has it's interactive. You can click on each one of the elements on the periodic table. Now, when you look at all of these, is there anything about all of these symbols? So the symbols, could anyone add to the chat? What's something that you notice about these symbols? And I'm looking for kind of anything. Or maybe like what's a pattern that you notice about them? Okay, grouped by colors. We've got an organization of the periodic table based on colors. Yeah. Similar properties. I like it. Numbered. Absolutely. Um, we've got a numerical order. One of the things, if there is two letters, only the first letter is capitalized. Absolutely right. Yeah, reactivity. Man, you guys are knocking this out of the park. Great job. So if you look at all of these symbols, there's kind of a pattern. Like the first few, the single letters are, kind of all going to be in the, not exclusively, but, the single letters are found in the first so many elements. Now, the next thing is if you have two letters, well, the first is going to be capitalized and the next is going to be a lowercase letter. Now, thinking about that, I want you to answer this question. Which of the following is an element? A, C, or sorry, I've got my display is a little bit different from how it appears on the Zoom, and I apologize for that. Is it C capital or capital key C, capital O, capital N, capital O, capital C, lowercase o, or none of these? And the super popular answer, which Hayden, make sure that you answer in the poll, is going to be capital C, lowercase o, because that is an example of an element. These right here, CO and NO. Well, that's carbon and oxygen. Nitrogen and oxygen. That's two elements. When you have two elements, these are compounds. So two different atoms coming together to make compounds. This one, however, capital C, lowercase o, that is an example of an element. Okay, now our elements are all arranged in order of their atomic numbers. Number one, we move across, and then we go down 3 to 10, 11 to 18. Now, this is the model of the periodic table that we have that has been kind of the most popular one for the better part of, over 100 years now. There were other organizations of the periodic table historically, but this is the emerging one now. Now, these are all elements that are, these are all organized based on their reactivities. Now, this first row right here, we've got lithium all the way down to something known as Fr or francium. The reactivity increases as we go down. Now, this video right here, I'm not going to play it in the interest of time, shows if you took pure lithium and you added it to here. And so what that means is Li as a solid, or Na as a solid, or K, potassium as a solid, added those to these glasses of pure water, a reaction would take place. Now, you can see these are little bubbles here that are forming because of this reaction. This right here, potassium, is basically starting on fire, and that's in water. So potassium is extremely reactive. Now, lithium to sodium to potassium, down to cesium and francium, those are going to be even more violently reactive. Okay, so the next thing that we're going to do for the next few slides, cesium thrown in rivers, is a fun time. I think that that's a. I think there's an episode of The Simpsons where Homer goes, he takes Bart fishing, and they use like a car battery and shock the shock the pond and kill a bunch of fish, and then they scoop them up. I'm envisioning that as another similar way. I've never thrown cesium in a river, but I would imagine it'd be very loud. Um, okay, so here what we have are different elements organizing together to form different molecules. We've already kind of talked about these. This is a compound and it's a molecule. Compound and a molecule. We have one oxygen and two hydrogens, water. Here we have one carbon and two oxygens, or carbon dioxide. Now, we can write the formulas for substances like this right here. So if you look on the screen, it's got a lot of stuff going on. Actually, in the interest of, let's see. Okay, I got two questions that are going to pop up right now. And I'm going to leave those up for a minute, then I'm going to do the closer questions. So this is a formula for the compound known as caffeine. All that we do to convert this, what is known as a structural formula, to a handwritten formula is we count up the number of atoms. Carbon, carbon, carbon. That's 3, 4, 5, 6, 7, 8. 8 carbons, so C8. Oxygens, I'm going to go, or actually I'm going to go to hydrogens next. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C8H10. So carbons are done, hydrogens are done. Now I'm going to go on to oxygen, 1, 2. Okay, oxygen is 2. And last but not least is nitrogen, 1, 2, 3, 4, and 4. Okay, I'm going to stop the mid question. The question was, how many hydrogens are in ibuprofen, which is our next slide. It says 18. The correct answer is 18. Now, after that, this is a different number, 3 out in front. How many are in the expression 3C13H18O2? Well, there's 3 of them. So we multiply this by 3. So that gets us 54. Now, I'm going to end this poll to open up the closers. Okay. We're going to pick up with some of these things at the beginning of our next class, but please answer the closer questions. Does the quiz today have material from chapter 3? No, it does not. The quiz today, as is the case, all of your quizzes is only, sorry, all of your quizzes are only going to be over stuff that we've already completed. So that quiz opened up this morning at 8 a.m. So it had stuff from last Wednesday, and that's where it stopped. It won't have any stuff over, it won't be over any of this stuff. Okay. I'm gonna let you guys just answer the closer question. I'll leave that up for the next little while. We will start class on Wednesday, going through some of this stuff again, looking at these formulas and converting them. But other than that, I hope you guys have a wonderful day. I'm sorry for rushing the last little bit here. That won't happen again on Wednesday just because we won't have to do quite as much review or quite as much about density and stuff. Okay, well, I'm going to end my share and I will start class Wednesday talking about these closer questions and giving kind of a review of those. So answer them and have a great day. Thanks for coming to class, everyone.